All right, good morning, everybody. My name is Arie van der Hoeven. I'm a principal program manager, new to this role on the Azure team, working on Denali with Laura here. And I just wanted to say a few words before we get started, before Laura gets started with her more in-depth talk. First of all, I am the program manager, so I'm running the how things get done, whereas Laura and the engineering team are very much working on the what and the details. So if you need to get in contact with me, you have questions about the program, I encourage you to look me up on LinkedIn. I'm out there. This has been an exciting project, and I've actually run out of business cards, so I apologize in advance for that.
I've still got some, and you can get to them through me if you need.
Okay, I'll just put my name on Laura's card, but she'll always direct to me for any kind of partner outreach. We work very closely together. I assume most of you saw Kashagara's talk yesterday. I'm not going to repeat all the points he made, except to say that we're very excited about this new model we're pushing forward, where we're really trying to move aggressively towards a standard that we then hand off to the industry. And we want to do this in a collaborative way with a good sampling of our partners. So this is, although we're here as Microsoft, and Laura's done a great job of kicking this off and working with the industry already. This is certainly something we're going to be handing over, and potentially by the end of the year. We're very aggressive in the schedules we want to hit with Denali, and we're seeing a lot of momentum, as you can guess. And this is great that we have a full room here. Apologize we didn't have more seats, but it's great to see a lot of familiar faces here as well. And with that, I'm just going to kick off and let Laura get started on her part.
Great.
Thank you, Laura.
Arie. Thanks, Arie. So my name is Laura Caulfield, and I'm a developer in Microsoft Azure. Today I want to tell you about some of the technology trends and application requirements that I've seen in my role driving, designing solid-state storage for our data center applications. And then I'll also tell you about the interface changes that we're adopting to support cloud-scale workloads. So we'll start out with a brief primer on current Ssd architecture and the priorities of today's cloud applications. Next, we'll dive into the prototype that we've been building for use across Azure. And then finally, we'll wrap things up by exploring the current state-of-the-art interface between the host and drive that we're driving forward. So we'll start out with the design principles that we apply to all of our cloud hardware. First, we need to support a huge variety of applications. Azure alone has over 600 different kinds of services, so there's quite a lot of diversity out there. We also have incredible scale, which means a healthy supply chain is critical, and we need hardware from a diverse set of hardware vendors. We also want to enable new generations of NAND technology as soon as possible, and unfortunately, current SSD designs have such complex interaction with workloads that this is a very challenging prospect. And finally, we need our hardware to be very flexible so that our software can continue to evolve at a rate that's much faster than our hardware schedules. So now that we understand the environment that we're working in, let's flip over to the SSD side and see what the technology provides. Inside of our SSDs, of course, we have NAND flash technology. This is the primary component. We also have quite a bit of DRAM. For every terabyte of flash, we need roughly a gigabyte of DRAM, mainly for that address map. So you might imagine the host having 4 sequential streams of I/O coming at the device all at one time. As the data comes in, then the SSD caches the information, and it continues to cache until there's enough data to fill a single page of the flash. At that point, it updates the address map and writes the data to flash. The 4 streams continue writing data until the drive reaches a point that's almost full. And by this point, some of the data has been overwritten, invalidated, and some of the applications, for example, the red one here, might have completely vacated the device. Now, unfortunately, these applications were running at the same time, so all the data is intermixed. So in order to free up some of the space, we can only erase at a block level. So we have to move all the valid data out of a block into a new block. And this is what we call garbage collection, and it can incur quite a bit of write amplification. Write amplification is enemy number 1. Anything we can do to reduce that will give us more bandwidth from the raw flash, and it'll also give us more access to the limited endurance of our SSDs. So one of the designs we explored early on was simply caching up enough data in the host so that we write out a large enough chunk so that the device invalidates the whole block at once. So you might look at these numbers of the drive and say, well, the blocks are 4 megabytes, so I'll just cache up 4 megabytes of data for every application, write that out at once, and then sometime in the future, it'll all get freed at once, and we won't have these annoying holes. So we expected writing 4 megabyte random IOs to the device might get us a write amplification of 1. We explored what the actual hardware was doing and found a very different picture. 4 megabyte IOs that were randomly written to the device weren't a huge amount better than 4 kilobyte randomly written IOs. And it took a gigabyte of data, caching that up, before we saw the write amplification that we were hoping for. Now this might be okay if we have 4 applications, but if we scale up to the hundreds and thousands of sequential streams we want in every drive, then that amount of DRAM becomes untenable. So this is at the heart of a fundamental design trade-off that drive designers make very differently from cloud system designers. So let's take a look at the perspective from the SSD design first. What's actually going on here? Your NAND flash isn't just one die, it's actually an array of many dies. And so as you write data to your SSD, it actually caches up much more information, enough to fill up 1 page in every die in the device. And this is a valuable thing to do for the SSD because it allows it to produce the highest throughput for a sequential write operation. You can also think of this as the drive being optimized for a single application, sequential writes. Unfortunately, for the host side, we have many more applications than just that one sequential write pattern. And if we look at the way NAND is scaling, this trend isn't likely to go away. It's only going to get worse. Because as we increase the capacity of our dies, the block size also increases quite a bit. So this is the SSD. Now let's take a look at what the applications are doing and how they would ideally like to map their data to the underlying structure of the NAND flash memory. The first of these applications is the Azor storage backend, often called the streaming layer. And this is a low tier in a storage hierarchy. So by this point, the data has been organized a little bit, and we have some control over sizes that we write, sizes that we read. The application needs to have really good write throughput, but it can get this by having lots of tenants running at once. So any given stream doesn't have to be very fast. It also requires a good read latency, and read latency at the user level, and they achieve this in their design by having a small reclaim unit size. So this application maps very well to what I call a vertical stripe, where each individual stream is mapped to a single block on its own die. This gives us high throughput by scaling up the number of streams on the device, and it also gives us the smallest effective reclaim unit size. Our next application is running in a virtual machine. This might be a legacy application with small updates that are bursty, and the user of the VM expects the full performance that it would see from a normal SSD. So this application maps well to a horizontal stripe, where each VM is scheduled to one block in all the dies, and it's scheduled to different blocks from the other VMs. So we have not only the high performance of using all the dies for the single application, but when a VM is cleaned up, it doesn't create the holes by being intermixed with other VMs. Our final application is also one that runs in a VM, but this one might have been redesigned for an architecture like this. So in this case, the application is still scheduled to one block on each of the dies, but from there it's able to further divide maybe it has logs that it can put each log on an individual die. So when a single log is cleaned up, then it doesn't create holes. So here's kind of a smattering of some of the different workloads that we see in the cloud. For the best flexibility, we would ideally like to be able to put all of these different type of applications in the same drive at the same time. Now there's a few other things I want you to notice here before we move on. As we scale up the capacity of our drive, we're not scaling up the size of our IOs, right? That application running in the virtual machine isn't going to suddenly double from 4K IOs to 8K IOs because we've doubled from 1 terabyte drive to 2 terabyte drives. We also aren't changing the host level policies with each NAND generation, right? We don't want to have to recompile or have a different type of driver or application for every different type of NAND generation that we have out there. So all we need from our interface are a few things. We need to expose many, many logs that are as small as possible. We need control over data placement so that we can set up those horizontal or vertical stripes. And we also need the management of the NAND physics to be completely hidden from the host. So with these ideas in mind, our next step was to work on a proof of concept. We evaluated the application's priorities and the technology trends, and we started to have some ideas of what this new interface should look like. So before I get into the prototype, let's level set on some terminology. We have, you've probably all heard these terms before, but they have very specific meanings when I talk about them. We have open channel SSDs, which actually expose raw physical addresses. Denali SSDs are an evolution of this idea, where we're exposing logical addresses, but still retaining the hierarchy of information. So we still have an idea of channel level isolation or die level isolation. We have flash translation layers, which in a standard SSD encapsulates all the algorithms that go into the firmware on that SSD. The FTL consists of two major components. There's the log manager and the media manager. And the log manager's job is to receive random writes and emit sequential writes. To do this, it usually has to use a map and to perform garbage collection. And the media manager does everything that has to do with the physics of the NAND. This will change with every NAND generation, possibly. And it does things like error correction, read, retry, scrubbing, and a whole host of other things that us cloud providers don't want to have to wrap our head around. So when we look at the evolution of our SSDs, we start with our standard SSD, everything in the drive. We have open channel SSDs with everything up in the host. This was the first simple step that, in fact, we've taken with the prototype as well. But the final solution that we want to take to production is Denali, with these two components of the FTL separated out between host and drive. Now we have a couple reasons for going with the open channel design in our prototype. It was very quick to do, and it gave us an upper bound on the overheads and worst case performance that we could see out of the system. It also gave us a chance to move all these algorithms into the host and have a much more flexible environment to explore for that new boundary between the log manager and the media manager. So without further ado, here is our prototype running. The hardware is over there on the right, and then there's a few screenshots of it appearing in the system. Our management software in the bottom corner there shows the drive as an open channel drive. And then the combination of changes from the driver and the firmware mean that we can run legacy storage applications on top of the system. For example, FIO or disk speed, or in our case, store score. So we took store score and ran a bunch of different kinds of workloads on the SSD and looked at the following results. First thing we wanted to look at were the overheads. What kind of write amplification, memory usage, and CPU would we have to spend in order to do something like open channel or Denali? And we found results that were not surprising to us, right? Basically, all the overheads moved from the drive to the host, and the magnitude of them stayed about the same. The major exception there is the CPU usage, and that's simply because the cores we have in the host are much beefier than those you have in an embedded SoC in an SSD. These overheads are also at a maximum, right? The algorithms were designed with a firmware mindset, and if we were to adjust them for software, then they could be more efficient. They also haven't been optimized for taking into account information from the applications. So now with the overheads and algorithms moved into the host, we have the chance also to optimize these and bring them down. The second thing we looked at was the performance of the system. So first, of course, looking at throughput, we looked at the standard four corners, read, write, sequential and random, and then a random mix of reads and writes. And the open channel SSD did very well compared to the baseline standard SSDs that we've been using. The read performance was much better, and the write performance, although a little bit lower, isn't of concern because the open channel SSD algorithms also haven't gone through the standard optimization that happens as the final stage before the product is taken to production. We also looked at the latency of our reads to the drive, and the key here in this workload is that we're also doing writes in the background. So this is a pretty challenging workload for any kind of SSD to implement, but it's also important for our applications. And for this as well, the open channel SSD did very well. So with the proof of concept complete and the results very promising, then we were given the go-ahead to move forward with the next stage of productizing the Denali SSDs. And that next stage is working on the specification so that our hardware vendors can start building the hardware for us. In the final section of the talk, then I'm going to go through some of the highlights of that specification as it stands now. At the heart of the specification is this logical hierarchical addressing. And what we've done is taken the standard LBA format and simply divided it into 4 chunks. So we have a group number that maps to an SSD channel. We have parallel units that map to the dies, and so on. And the exciting thing about this new LBA format is that we're retaining the isolation guarantees that we had from the physical addressing, but we're giving the hardware a chance to do all the things it has to do to manage the NAND. So it's able to map out bad blocks transparently to the drive or to the host. The system can also perform what we call 2-part wear leveling, where the drive and the host share responsibility for wear leveling on the drive. If the drive is aware of the boundaries of a tenant, it can keep the wear even within that tenant. And then the host can swap the physical locations of tenants at opportune times for the application by telling the drive to do a copy offload. We also have some new requirements for the host that come directly from the way that NAND operates. So in particular, this is the block level erase and writing in order to the block. So the host must allocate a fresh block before writing, write in order, and then at some point later trim the block to reclaim space. And this is how we shift the garbage collection type algorithms up into the host. There are also a few pieces I'll go over the next slides that are new elements, the first of which help us abstract the NAND management so that the interface doesn't change even as NAND generations change. For example, we'll go into the cache minimum write size. So to understand this, we'll dive fairly deep into the NAND flash behavior. Off to the left here, we have a diagram of several memory elements within a TLC flash. Each row is a different NAND cell, and each column represents a different bit in that NAND cell. So we have 3-bit TLC NAND flash here. The numbers in the cells represent the number of the page that bit maps to. So we have, you can see from the colored squares that we've written up to page 18, and the next page that we're going to write is page 19. As the drive writes to the flash, each new page follows this diagonal pattern. And this is to improve the reliability of the NAND, cut down on write disturb. But the point for us is that at any given time, there are a number of memory elements that are partially written. And again, for NAND reliability, it's important that we don't read the data from those partially written cells because they're more prone to something called read disturb. So coming back to the interface, the one number that we're exposing for the drive to handle all this is called the cache minimum write size. And it's simply a number of kilobytes that the host has to cache, since its last write pointer, and read from that cache instead of from the flash directly. The drive could expose 0 kilobytes, which could mean that it's doing the caching, or it could expose some other number which represents or encapsulates the page size or the number of bits in the memory element. But the point is the interface doesn't have to change. We just have the one number, and the host queries that number and uses it in its algorithms. So this is one example of how we've abstracted the media management and allowed that to stay in the drive. We've also encountered some challenges that other new interfaces are tackling as well, and we're planning on leveraging the solutions that they're coming up with. One example of that is the fundamental trade-off between reliability and QoS. This has definitely come up in the I/O determinism forum. And what's going on here is the design for our RAID stripe. So in standard SSDs, we have essentially one tenant, right, striped across all of the dies in the drive. And so our RAID stripe is fairly simple and fairly low overhead. But as we chop this up into smaller and smaller tenants, then that RAID stripe shrinks and the overheads become more significant. And so we have this trade-off. We also have different kinds of users, as you saw. We have some that are very small and some that stripe across. And conveniently, those actually map well to who needs RAID as well, right? So our Azure Storage backend has replication at a higher level. So they're less interested in needing RAID, and they're the ones with the small tenants. The VMs, on the other hand, are expecting an old-style SSD and the reliability they get from that, but they're also able to stripe across all the dies. So what we need from our interface is a mechanism to choose which of these applies to which tenant, which seems to be coming out very well in the solution IO determinism has come up with called read recovery levels. So this concludes the highlights of our Denali specification. Just to wrap up the talk here, we saw technology trends and application trends and how we're combining those to build an interface for a long time into the future, hopefully. We also saw the results we had from our successful proof of concept and how that's encouraged us to move forward with our design. I'd like to encourage you to stay tuned over the next few months and next year, as Arie mentioned, and take part in the discussion. This is going to be an interface that needs to be built by the community because it's going to be used by the community in a lot of different ways. So feel free to reach out and read the articles that show up and generally keep the discussion going. Thanks for listening, and I'm happy to take your questions now.
Thank you very much,
We're happy
Laura.
to take your questions.
We have 5 minutes for questions, and if I would the next speaker please come so we can mic up?
Hi. I want to ask a question about any plan for standardization on the driver. If it looks like it's not going to be a standard MME, right? So are we going to standardize something for the Denali driver?
So interface-wise, we would like it to become standard, and so new technology can center around that. I don't think I can comment on Windows plans for the driver.
Yeah, I think the question of whether this goes to NVMe, that's a very great place for it to end up. Our goal isn't to create a, we have this joint development foundation group that really allows us to be agile and move quickly, but we certainly want to hand this off to the industry, and NVMe would be a great place for it. But again, we don't have a firm comment or commitment on that, and that's a decision to be made by the group who's members of this JDF committee.
We'd certainly love to see standardization in all aspects of this.
Is data movement associated with garbage collection done by explicit reads and writes from the host, or is that still inside the drive?
That would be in the host. So because of the way the requirements to the host to reclaim, write in order, claim, write in order, and return, that should eliminate all the garbage collection that's happening in the host, in the drive. And so the only data movement that should be happening in the drive are when we do a copy offload to do wear leveling, or maybe handling bad blocks or physics.
So, but the data movement associated with garbage collection then adds to the host traffic, host interface traffic?
It can. So if we just have it in the driver completely isolated from the applications, yes, that'll be the case. But the idea is that a lot of the applications are already doing this garbage collection. It's just at odds with the garbage collection the drive is doing. So we would like in the future for these things to be combined and reduce overall system write amp.
So we are thinking that in future flash memory, the size of physical block can change for each block. I think current open channel can support different chunk size. But
Yeah.
if your going to make a block mapping with logical chunk. Can this cause some problem, like changing the by swapping the blocks, and that that can change.
Yeah, so over time, then the block size will increase just because the way flash memory is developing. And we fully expect this to affect the chunk size, right? So in the startup sequence, then the host will query, hey, what's your chunk size? And then it'll use that information and it's basically map it to its reclaim unit size. Yeah. Any other questions?
Maybe we could take one more question.
Okay.
Got one here.
Take one last question, and then next presenters are ready.
Hey, Laura. The question was, in the keynote yesterday, there was alluding to possibly some middle controller at a layer above Denali. Can you speak a little bit about that? And will that be part of the standard?
The standard we're focused on is just the lowest possible interface between the NAND controller and the next level up. So this, I've been talking like it's a software level, like it's a driver, but it could be any number of things. It could be an aggregator, it could be an SoC. I mean, possibilities are endless here. And the point of doing Denali is to open up this space for innovation. So some people might want to put it in an SoC and build their own SoC with their own garbage collection and management across a larger array of flash. Or other people might want to stick with software and combine it with their applications. So I don't have a specific comment on exactly what will be produced, but the focus with Denali is to open up all these possibilities. We can talk more later, too.
Okay, thank you very much.
Thanks, guys.
Thank you.